All right, I think we should get started. Welcome to the Data Science Seminar from the University of Washington eScience Institute. As part of the University of Washington, we acknowledge the Coast Salish peoples of this land, the land which touches the shared waters of all tribes and bands within the Suquamish, Tulalip, and Muckleshoot nations. Today, I am pleased to welcome Dr. Eric Massanet. Dr. Massanet holds the Duncan and Suzanne Mellenchamp Chair in Sustainability Science for Emerging Technologies at the University of California, Santa Barbara. His research develops energy and materials systems models to identify technology and policy pathways for decarbonizing industrial systems. He's currently a lead author of Chapter 5 for Working Group 3 of the IPCC's 6th Assessment Report and a member of the Research Advisory Board at the American Council for an Energy Efficient Economy. He holds a PhD in mechanical engineering with emphasis in sustainable manufacturing from UC Berkeley. Today, Dr. Massanet will speak about data center energy use, unknowns, and how estimates are made. One thing I'd like to mention today is that this talk is co-sponsored by the Environmental Impacts of Data Science Special Interest Group at the eScience Institute and the Responsibility in AI Systems and Experience Group at the University of Washington. As usual, please use the Q&A feature of Zoom to ask questions. And with that, I would like to welcome Dr. Massanet to our seminar today. Thank you.
Well, thank you very much for the kind introduction. It's really great to be here today, especially to hear about the initiatives you have underway on responsible computing and the environmental implications of data science. So I'll be speaking about my research today in the world of data center energy analysis. It's something that I've been involved in for roughly the last 15 years. And I suspect that if you're here, you have some interest in the energy use and environmental impacts of data centers as well. And maybe you've heard or even read stories coming from the media about the energy use of data centers and how it's growing really rapidly. And if we don't get a handle on it, it's likely to use lots of the world's energy in very short order because we're spending lots and lots of time online. And perhaps you've seen even more specific articles about the environmental implications of email and spam being bad for climate change, or the increasing footprint of our digital habits and our streaming video. And these are all very logical conclusions one can draw, because when we think about data centers, most of us think of very large data centers like this Facebook data center that's in Ashburn, Virginia. This one is quite large. It's got 70 plus megawatts of installed power capacity. That's enough for around 50,000 homes. So when we think about, the size of data centers and how much energy large data centers use, and we couple that with our own, observations about how much additional time we're spending online and reading about how the world is becoming increasingly interconnected, it's quite logical to assume that the energy use of data centers must be rising rapidly. And data centers, at least the large ones, are only getting larger. So I just brought up an image of the Switch Citadel campus data center, which is in Nevada. When it's finally built to its full capacity, Switch estimates that it may have as much as a power draw as 650 megawatts, which is quite enormous. So there are big data centers and there are huge data centers. And these are the ones we tend to hear about when we think about the environmental implications of the internet or of data. And the truth is there are many of these large data centers out there. So the really massive ones, which are known as hyperscale data centers, these are tracked by analyst teams. We have around 600, by now probably close to around 700 very large hyperscale data centers. That's a picture of a Facebook data center in Prineville, Oregon. Maybe you've seen a data center like that driving down the road or on the outskirts of your city. There are also a lot of very large standalone data centers that are run by co-location companies or cloud companies. Even some large companies that have a lot of data needs have very large enterprise data centers. These occupy large buildings, sometimes even campuses, and you may have seen some of these because they're very, very visible. The truth is, for every one of these very large and very visible data centers, there are many, many more that we don't see. And these are what we call on-premises data centers. And they can vary greatly in terms of their size. So, a lot of companies and organizations have data centers for supporting their business practices. They can range from even enterprise class data centers, the top picture there on the right, to very small data centers, server rooms and server closets that are located in many office buildings around the country and around the world. Estimates suggest that there are millions of these types of data centers out there. So the problem could be even greater than the data centers, that are visible to us and that we hear about in the media. And the truth is, there's not a lot we understand well about these many, many millions potentially on-premise data centers. But some close colleagues of mine at Lawrence Berkeley National Lab have done some really great work here in the US. And they've confirmed that, yes, there are lots of these small data centers by looking into commercial building energy consumption surveys that are published. These data are from 2012, so already they're about 10 years old. But Lawrence Berkeley Lab found that there are many, many so-called small data centers. These could be rooms or even closets, 1.7 million of them in the United States. And as you see on the map here, which kind of plots out their density, no surprise, they're located in areas of large population and economic activity around the country. But they are quite small. LBNL estimates that a small data center, which accounts for the lion's share of small and mid-sized category that are on premises, those data centers on average have just 2 to 3 servers. So that's not to say they're not important from an energy use perspective. They're important very much so from an energy use perspective, but also in terms of, the fact that they're not visible to us, even as energy analysts, someone like me, in a very clear way. So I'm speaking to you today as a member of a small but growing community of researchers which are in the field of data center energy analysis. So what is it that people like me do? Well, we have some common research activities, goals, and questions that we're often asked. And the most common one we're getting, and trust me, this is coming nearly every day, given the raised interest in the energy use of the internet. The biggest one is always, just how much energy use do data centers use? It could be for a region like the United States or Europe, for the world, for China, but we're often asked to put a number on this, this area of energy use globally. We're also asked to make projections about how data center energy use may evolve in the coming years. We all know we're using digital services much more than we used to in the past. The truth is, a lot of the world still is not connected. So there's a lot of interest among policymakers, both regionally and globally, to get a sense of just how large data center energy use and where is it going. And then, of course, once we can make these kind of estimates, there's a lot of interest in how to improve, how to change the trajectory of data center energy use. And for answering all of these types of questions, I wish I could tell you that we rely on wonderfully rich and validated data sets on energy use and data center installations. But the truth is, as you'll learn today, we rely really heavy on computational models due to a lot of pervasive data gaps, which I'll discuss next. So this just gives you a sense of the sort of questions we hope to answer around data centers. And for those of you who might not be familiar with a data center, we look at data centers at a fairly simplistic level in a lot of the models that we use. So here's a sketch diagram of a typical data center. We see power coming into the data center from the outside world. There's equipment that's necessary for ensuring backup power supply, both outside the data center and within the data center. So an uninterruptible power supply is a device that has battery banks in it, and it can guarantee that the servers and IT equipment will stay running through short power outages and maybe even up to 30 minutes or so. There's cooling equipment to remove the heat that's generated by the IT equipment. But we generally divide the data center into 2 broad buckets. The first and really the most important one is the IT equipment itself. These are the servers that do the computations, that provide us with the database queries, that host the websites and so forth. This is the real work happening in a data center. There are also many storage devices, both hard disk drives and increasingly solid state drives out in data centers, and then network equipment for routing all the information around both within the data center and back out into the internet. Everything else above this line is something we refer to as infrastructure equipment. It doesn't do any useful work for the services of the data center, meaning it doesn't provide me my search results or my streaming video from Netflix. Rather, infrastructure equipment keeps the data center cool, keeps the IT equipment within an acceptable temperature band, and also provides stable power. And there's a metric that we can use often in the energy analysis community, which is something known as PUE. It's the power utilization effectiveness. And it's a simple ratio that a lot of data centers are now reporting, where in the numerator, we have the total power coming into the data center. That's the sum of both IT and infrastructure power use, divided by the IT equipment power use, what we really care about, right? Data center operators treat all the cooling and power provision, energy use, and cost as overhead on their core business purpose, which is the IT equipment providing data services. And there are a lot of companies that are now reporting these data. I've given you a selection here of just a few. The theoretical minimum is 1. So ideally, a data center doesn't want to pay for power that's not used by its IT equipment. In reality, we have to expend some energy on cooling and power provision. And the big, often hyperscale data centers, they have really well-engineered data centers and cooling systems, which brings their PUE pretty close to 1. This blue line shows the trends in sort of the average data center, which are tracked by the Uptime Institute. This is a think tank, an analyst firm that studies and provides data for the data center industry. And what we see here is that going back to the early days of when the policymakers and the data center industry really started looking closely at their energy use, the PUE went from a really terrible ratio of about 2.5 on average. That meant that a lot of energy going into a data center was just going to cooling and power provision and not to the IT devices themselves. Most data centers have brought that down over time, but the Uptime Institute has observed kind of a plateau in increases in cooling and power efficiency. So the average is around a 1.6. And we also track other data centers. I'm just giving you a few data points. So for example, IBM has a lot of legacy, in-house on-premises type data centers for which it's very hard to bring the PUE down to like a Google or a Facebook level. But having this sort of information gives us at least some high order sense of how energy is used in a data center. So this pie chart I just brought up is a real world data center. It's the Facebook Prineville data center. They report their total energy use. They've also reported their PUE in the past. So from that, we get a sense of how efficiently they're cooling the data center and just how much energy at that data center is going into the IT equipment, which provides the useful work. And we can contrast that with, smaller data centers. This is a hypothetical, typical enterprise data center that has an IT capacity that's 1/10 the size of Facebook's IT capacity, but you might expect then that it would use 1/10 the energy, but it doesn't. It uses a lot more. It uses 1/7 the energy because of the higher PUE and the generally inefficient power and cooling systems. So just by having, this PUE metric, it tells us something about how data center energy use is used, and a lot of companies are reporting it. But clearly it's not enough, right? Because it only tells us about the overall efficiency of a data center's cooling and power provision. So which data do we have in the analysis community, and what do those data actually tell us? So I just gave you some insight into, PUE and what that tells us about data center energy efficiency. But I want to take a step back and think about the energy use of data centers as a sector. And the truth of the matter is there's no global or national or frankly, even regional energy statistics that are comprehensive of all data centers, the hyperscale, the cloud, the colos, and the on-premises. What you're seeing here to the right, this is our latest commercial building energy survey in the United States. It's from 2012. We hope to get 2018 results soon. But data centers are conspicuously absent from this. We do a great job of tracking energy use by all sorts of building types, except for data centers, because there has been a historical barrier to getting data centers to report information because a lot of it is seen as proprietary, right? So in the US, in Europe, pretty much everywhere in the world, we don't have real data reported data on the energy use of all data centers. That's not to say we don't have a picture of parts of the system. So in my research lab, we've been tracking the reported energy use by data center companies and tech companies. And I'll give a little plug to a website that we'll be releasing soon. It's not quite ready yet, movingbits.org. We hope it'll be ready in a few months. But we've gone through all major data center operators and pulled out their reported energy values for as long as they've been reporting them. And the good news is there's a strong positive upward trend for companies that are in the data center space reporting their energy use. And I've given you a sample here, and these data are for 2018. So Google, Microsoft, IBM, Apple, some of the really big players are being transparent about their electricity use. However, a key caveat is not all the reported data are for their data centers. Only a few companies, which you can see here indicated by the asterisk, actually report the energy use of their data centers, and some even report the energy use of individual data centers. But it's a minority of companies that do this. The rest tend to report their electricity use as an organization. So for a company like Google, we know from just anecdotal information that most of Google's energy use is likely going to their data centers. So at least we get an upper bound, but it doesn't give us a precise view. And the number of companies that we're adding to this list is growing. So that's the good news. And based on this data, it's really clear that that segment, large data centers, often standalone data centers, their energy use is rising. So I've graphed here some of the recent data we've collected for Facebook, Google, and Microsoft. All three, mind you, they have different scopes, whether they're reporting for data centers or for the whole company. But for all three, their energy use is going up pretty rapidly over the last 4 years. Facebook's has more than tripled. Google and Microsoft, that's more than doubled. So we know that for this segment of large data center operators, it's very likely that their energy use is rising based on the reports that we're seeing. So we get some insights into those large data centers through company reports. There's also a number of analyst firms, market analyst firms, data center market firms, real estate firms that also track the data center market. And what they tend to do is report on the installed or designed IT power capacity. So this is not the actual electricity use. This is usually the maximum IT capacity of a data center, but it gives us some idea, again, an upper limit of the energy use of co-location data centers or cloud data centers, which is a good thing. And we see from those data, for those dedicated data center builds, it's apparent that their energy use is rising as well. The installed power capacity, as you can see here, this is a bit of a busy graph, but what it's showing is trends in the net absorption of data center space in terms of installed megawatts of critical IT power, and then the builds that are happening from year to year. So it's clear that that market trend segment is trending upwards as well. I will note, though, that there is some double counting between what these firms track and what the companies report. Just so we don't mix the two and assume that they're mutually exclusive. For the rest of the data center sector, all those small data centers, all the enterprise data centers, my campus here at UCSB, we've probably got dozens of data centers in different buildings that are quite small. There's really little information or no information on those types of data centers. What we get is a patchwork of insights. And what we're seeing is that for that broad segment of data centers, over time, they may not be growing rapidly because a lot of their data services have shifted to the cloud over the years. So for example, my university uses Gmail. So we no longer have, campus dedicated servers for UCSB email. They're sitting out there in the Google Cloud, and Google provides that service to us. So what you're seeing here is some information from Cisco, who tracks the internet market and the data center market. Their data has suggested that really most of the growth is in the hyperscale and cloud data centers, and there hasn't been much growth in all those hidden on-premises data centers, at least nothing like we're seeing in the other segments. So you're getting the sense that we've got bits of information that are telling us different things about different segments, but no comprehensive statistics on the whole. And therefore, what you need to understand is if you see a data center energy use estimate reported in the media coming from a researcher like me, If they're at the regional or global scale, they're all coming from models. So what you see here on the right is I've adjusted the scale here to the range of estimates that were published in 2008. So all those reported data center energy values, or at least the tech company values, those have shrunk down, right? There's this huge gap between what's being reported and what the models have estimated as the global data center energy use. And there's a threefold difference in the range of estimates. So a really broad difference in the range of estimates that are coming from these models. And I'll explain to you why that is in the next few slides. So let's talk about how do people like me and other analysts estimate data center energy use. In my opinion, the most robust, I'll cut that out of the recording later. The most robust models are ones that we call bottom-up models. These are models that try to estimate the total number of installed servers out there in the world or in the United States, the total number of storage devices, the total number of network devices, all the equipment that goes into data centers. Just what are the counts of those, those different equipment types, the different types of servers and devices. If we can understand the installed base, that's the acronym IB, it gives us some sense of the scope of the data center sector. Imagine doing this for buildings. We do this for buildings when we analyze buildings. We want to know how many square feet of different buildings are built out there in the residential sector or the commercial sector. We want to know the number of cars on the road to estimate the energy use of the transport sector. Bottom-up models for data centers take a similar philosophy. So we first have to establish just how many devices are out there in the world's data centers. I'll talk about how we do that next. And then the second piece of the math is that we have to establish what we think are typical power draw values for servers, for storage devices, for network devices. If we can do that, we can estimate the total IT electricity use. And if we can make some estimates about PUE, either coming from reports or physical models that I'll discuss later, this is how we arrive at so-called bottom-up estimates of data center energy consumption. My colleagues and I at LBNL, we've done this for the US. We've done this for the world recently. Other groups around the world use these bottom-up models, and they're seen as being the more rigorous type of model because we try to account for all the equipment in comprehensive bottom-up fashion. And if you've seen reports on data center energy use from the United States, they're coming from LBNL, they're coming from this bottom-up model that I just showed you. And the most recent study we have is from 2014. And you may say, wow, that's really old, right? It's 2022. Why is it that the latest bottom-up model we have is from 2014? I'll discuss that next. But first, you take a look at kind of the technology detail we get in these models. If we build them well, we can analyze trends over time and explain how energy use has evolved as functions of the types of devices installed, how much of it is servers, how much of it is storage, how much of it is network. We can also present, energy estimates for different types of data centers. Hyperscale, closets, internal data centers. So these bottom-up models give us a very technology-rich view of the data center space, but they require lots and lots of data. And that's one of the reasons you don't see estimates like this coming out very often. So in the LBNL model, which we use, how do we estimate the number of devices out there? Well, there are market analyst firms like Gartner, IHS, IDC, who track server shipments and storage drive shipments and so forth. They have a pretty good view of all the devices that are installed out there because that's their business purpose, is to provide that market intelligence. Unfortunately, their data are often proprietary. You have to buy them, you can't share them, but that's generally where we get the data on all the installed IT hardware. On the power side, there's more uncertainty. So where do we get power data on all those various IT devices and for PUE globally or at the national level? We tend to have to rely on a patchwork of information and integrate it into what we think are robust estimates. That includes, having server power measurements coming from manufacturer databases, sometimes using manufacturer spec sheets. We often have to conduct industry surveys to ask different data center operators if our assumptions are correct. We rarely get the exact numbers from them, but they can tell us through expert elicitation whether or not our assumptions are reasonable. And we use a lot of estimation. So these types of models, even though they're quite robust, we think, they're granular, they give us a lot of insights, there's a a lot of data and a lot of assumptions that go into them. And depending on which data sources you're using and which are public and which are private and who you ask, these types of models can give different answers. So what I'm showing you here in this comparison table is a comparison of two studies. A recent global study that's got my name on it. It's there in the second column, where we looked at the trends and through 2018 in global data center energy use. We also looked at different regions. So we looked at Western, Central, and Eastern Europe based on the data we had, and we couldn't really distinguish which countries were in that group. And we came up with an estimate of about 46 terawatt hours for that region in 2018. A few months later, a really great study came out of the European Commission looking at the EU 28 using a nice bottom-up model, but based in Europe. They came up with an entirely different estimate, 77 terawatt hours. And that's a pretty significant difference. And when we dug into the assumptions that both teams were making, we could see that based on different data sources, different assumptions for server power, different market analysts we were turning to, we had key assumptions that differed quite heavily or significantly. And what I'm doing here is just for a quick eyeball comparison, indexing to our assumptions. The European Commission study generally had higher numbers for installed number of servers, server power. The only place that they had an estimate lower than us was for the energy use related to different storage devices. So even though we have different bottom-up models out there, their results depend heavily on the data sources they're using, and there's really no global consensus yet on which data sources to use, even for the same region, because there are many data gaps. So these bottom-up models, which my research colleagues and I work on and are improving all the time, their advantages are that they give us this really technology-rich view. We can really explain what's going on, and we can use them to also answer that question about where energy use might be going. And since we're representing technologies, we can often make assumptions about how they can be improved. So these types of models are really great for providing guidance on how data centers can save energy and emissions moving forward. But their disadvantages are the data requirements are really substantial. It takes a lot of time and resources to conduct these studies. Often the data are costly and proprietary and can't be shared. And that means that these types of studies don't happen very often. And that's why you're seeing a result for the US from 2014. So what's happened is other researchers and other methods have come into the field to try to fill in the gaps between bottom-up studies, because they only come out every 3 or 4 or 5 years. And clearly the world wants to know about data center energy use on much finer timescales than that. So in the early days of this field, there were just a few estimates at the global level. So I'm giving you global results here. And it's my colleague, John Kumi, who was really the pioneer in estimating data center energy use at the global level. And he produced 3 different studies, and you see the trends here for different time periods up until about 2010, using a bottom-up modeling approach. But around that time, interest really started rising, and more researchers started becoming interested in the energy use of data centers. And so we saw the emergence of what I'm calling here top-down analysis. What does that mean? Well, I'll give you a couple of examples from a couple of approaches that are cited quite often that have been used to fill the gap in time between bottom-up studies. So one highly cited model is from Anders Andre. I just updated the number of citations today. His model predicts these sorts of trends. And as you see from the model construction, the reason we call it top-down is because it takes the electricity use of data centers in a base year, often coming from a bottom-up model, and it tries to move it forward in time on the basis of high-level indicators. So in his model, he uses global IP traffic as a driver of growth and moderated with a factor to account for energy efficiency in data centers. So the construction of the model is quite straightforward, and it tended to predict a large rise in energy use because the demand for data center services as measured by IP traffic is rising rapidly. Another model is a bit simpler from another research group where it was making projections on the basis of economic growth for the sector. So at what rate are we building and investing in data centers? It's another indicator that is freely available, and we have it readily available anytime we want to conduct a study. So the benefits of these top-down studies are that They're simple, they're transparent. We can conduct them using pretty readily available data on activity indicators for the sector, but they often tend to project large growth in energy use. And in fact, when my colleagues and I produced a new global study for 2018 using the LBNL bottom-up model and a bunch of new data sources, our model estimated that the data center energy use globally hadn't increased drastically since 2010 due to large efficiency effects. But you see here a big spread in the numbers coming out of the analyst community. And so hopefully you can get a sense for why these differences exist and how the field needs to improve its ability to predict and estimate the energy use of data centers. Because a 4x spread in results can be confusing to policymakers. It can be confusing to the public. So these top-down models, like I mentioned, they have advantages in being, quick and easy and based on readily available data. They're often anchored in bottom-up estimates, but they're fairly simplistic and often they can miss technology efficiency that bottom-up models will catch. And small errors in the rate of growth can really compound over time. There's a third class of models, or I should say estimation methods for coming up with data center energy use totals, which is based on the installed capacity of data centers. So if you think back to one of my early slides, I mentioned that analyst firms track the installed capacity of different data centers. These are mostly, the standalone large data centers and not so much the small data centers embedded in office buildings. But they can do this on the basis of public records. They can do this often on the basis of the uninterruptible power supplies that all IT devices need. What's the capacity that was sold in a given year and installed? So this approach also relies on fairly readily available data, but often they have to make assumptions about just how much of that IT capacity is actually used. And we know from looking at real data centers, especially data centers like colos and leased data centers, that it's rare that they use 100% of their capacity in any given year. It's often much less than that. So this is another approach based on publicly available data, leading to different advantages and disadvantages. Here again, this is based on readily available information. It's fast and easy to generate. You can use surveys to help fine tune some of the estimates. And it's useful for an upper bound, because if we assume that the IT capacity that's installed in data centers is fully utilized, at least we get an upper bound on data center energy use. But it suffers from some of the disadvantages that top-down methods do, meaning that it's a bit rough. It can give us insight into broad trends, but we're prone to overestimate because we don't really know the true capacity utilization. And not every data center will report its UPS. We don't have information on the UPS shipments or the installed power capacity for many of those smaller data centers. And frankly, many of the big data centers don't use UPSs, central UPSs. They may have backup batteries at the rack level, and we miss those. So what does this all mean, right? So let's get back to the big picture. So I'm getting back to my original graph where I'm showing you, the reported energy use from a lot of the big tech players. This isn't all of them, but there is a major gap between what those big data centers are reporting and what the models are estimating. The bottom-up methods tend to come in a bit lower because they try to understand the installed characteristics of the servers, of the storage devices, of the network devices. So they're taking this really granular technology-centric view of data center energy use. The top-down models, which are often, extrapolation based on broad trends, they tend to predict energy use that's higher in this range. And the sort of, in-between ground of estimating data center energy use on the basis of installed capacity or backup power supplies or installed UPSs falls somewhere in the middle. But it's a really big variance. And we also know that there's a tremendous reporting gap. Some of this we can close for getting, by getting more companies to report. I'll talk about that next. But we know we'll always have a reporting gap because there's really no good way to gather energy data on those millions of installed small data centers. The closet down the hall from me, if I were on campus, in my building, probably isn't even separately metered than the overall building. So we're always going to have a reporting gap. So the real priority for researchers like me is We need to work on improving our energy analysis models and methods and data sources. So I'll just give you a quick take on my prognosis for where the energy analysis field is going and name a few priorities. And then I'll stop and it'll be time for questions. Okay. So the first is probably obvious to you. We need more reporting. Anytime I get the chance to talk to a data center operator or a tech company, first of all, if they're reporting, I say, thank you. It's very helpful that you're reporting your energy numbers. And if they're not, I encourage them to think about reporting. This is a message we often send to policymakers as well, right? So we can have voluntary reporting where more data center operators or even organizations that have data centers that aren't necessarily in the tech sector. GM has data centers, right, for its design centers and so forth. If we can get more reporting, we'll have better data and we'll have a better way to ensure that our models can be validated against real world numbers. So the trends that I see as someone who's been watching reported data now for 10 plus years is that there are positive signs for more companies reporting, but we're not there yet. There's an awful lot of data center companies that still don't report, and there are many data centers that may never report. But there is an opportunity that I and my colleagues are sensing for sort of a third-party, data arbiter, so to speak, right? So one of the reasons a lot of companies don't report is that they put a lot of engineering into their data centers, and the energy use of the data centers gives some clues about their installed capacity, what they're running on, and so forth, right? So other sectors have kind of solved this problem by having an independent third party. An example I use often is the cement sector. So they have an initiative called Getting the Numbers Right, which was set up by an independent third party, and cement companies submit their data to this third party. It's anonymized, and the third party will release kind of high-level indicators of energy use that don't reveal any specific company's energy use. I think that's a big opportunity for the data center sector. But there also are some promising developments on the regulatory front. So two that I'll just mention today. One is right here in the United States. In the Energy Act of 2020, which passed just at the end of 2020, there are some requirements in there that should move the analysis field forward. One is that there's a requirement for a new national US data center energy report. So I'm happy to say that hopefully, in the not too distant future, we'll have a more recent snapshot of US data center energy use, so we can stop using the 2014 picture and start using, a 2022 picture. And a lot has happened over that period. There was also some requirements for an open data initiative for federally owned and operated data centers. The federal government has quite a few data centers, and they contract with lots of data center companies. So the goal is to make those data a lot more open. So if we can get a better sense of how those data centers operate, we might be able to generalize more to the broader population. And there's some requirements for developing better data center efficiency metrics that could then hopefully encourage more reporting. Something really exciting is happening in the European Union in parallel. They released from the European Commission a draft energy efficiency directive. It's freely available online. If you take a look at it, you'll see that they're going a step further and suggesting that data centers above a certain size report on things like their installed power, their floor area, their incoming, outgoing traffic, total data storage. Having this sort of data would be a real boon to the modeling community because these are insights we rarely get coming from companies. So more data reporting is absolutely needed, and there are some positive trends in that direction. In terms of the modeling, one piece of the energy puzzle has always been PUE. Now, we get PUE data from different companies, but it only tells us, what their overhead energy use, what their infrastructure energy use is, and we don't get insights into, the granular details of why that PUE value is the way it is. So there's been a lot of progress made in models that can be pretty accurate at predicting PUE. So the determinants of PUE, what you see here is a schematic of one major type of data center cooling, which is a water-cooled chiller with a cooling tower, some economization. My PhD student developed this particular model, Noah Lay. And if we can pin down the different types of cooling technologies that are used at data centers, often this can be public information. The types of other equipment that are installed, we can generally get these from public sources like vendor data or manufacturer specs. If we get some sense of set points within data centers, a lot of data centers are open to sharing their set points. For the efficient one, it's kind of a badge of honor to say that they're running at higher temperatures to save energy. We can also get these from surveys. With this sort of information coupled with climate conditions, these physics-based models are getting pretty good at predicting pretty accurately the PUE of a given data center with a given type of technology in a given location anywhere in the world. And I'll show you some recent results which are under review now for publication. We looked at the United States. This is a map of the various climate zones. One nice thing about studying the United States is we've got a lot of climate zones. Most of the climate zones that exist in the world exist somewhere in the United States. And what we did was we used this physics-based model to use publicly available information and see if we could at least get a bounded PUE estimate and verify that against reported PUE values for different data centers using different cooling technologies and different climates. And the model performed pretty good. It gets within about 10%, which from a macro perspective gives us a lot better modeling capabilities for estimating PUE when we're trying to estimate the overall energy use of data centers within a given region. And the model also is able to predict water use because that's also based on mass and energy balances. We're not talking so much about water use today, but it's an emerging topic for the sector, a very important one, and there are metrics for reporting water use as well. So these physics-based methods are moving us closer to not relying so much on reported PUE values, because if we know enough about the general characteristics of data centers, we can predict PUE with reasonable accuracy. So that's the second nice trend that's good. The third area that's a big priority for the field and which we really need to move on is we're very dependent on reported data from manufacturers or data centers. And I'm proud to say that here at UCSB, we have an experimental data center that is now off the ground, and it gives my colleagues and I the opportunity to take our own measurements. And I see this as an important contribution from energy analysts to get a better sense of some key questions. If we can hook up power meters to servers, we're less reliant on benchmarking results from manufacturers, which are great, but they're often skewed to their very best server model. We can conduct our own empirical measurements and look at different server configurations, more or less memories, different types of chips, different applications and workloads. And this is a trend that I think is going to be an important one for generating our own numbers on server power use and storage power use and so forth. And it also would give us the opportunity to stay one step ahead of new emerging technologies. And this has been a challenge for all of us. We're often asked, well, what is the implication of artificial intelligence for global data center energy use? And the honest answer is we don't really know because we don't have great data on the energy intensity of different types of artificial intelligence model training with different types of processors. By taking our own empirical measurements and working with computer scientists and electrical engineers, it's sort of the next frontier for people like me to generate data that will allow us a much better view of the granularities of energy use by hardware, by software, and by application to make our models more accurate. And frankly, that's what's going to be required because looking forward, our models in general are better at looking backward because we can generally get historical data because we have reports coming out, from companies on how much energy they used and so forth. But forward-looking analysis is quite difficult. And why is that? Well, the models are always balancing this tension, which I've depicted here on this seesaw diagram. On the one hand, we know without a doubt that data center the demand for digital services from data centers is rising, and it's not going to go any direction but up, right? With the emergence of AI and increasing applications, one of the reasons we think Facebook's energy use is going up so much is due to their artificial intelligence. I think they've said that publicly. A big swath of the world still isn't connected. That's a bad thing. We want everyone to have access to basic digital services around the world, but that's going to create additional demand for data center services. We have population growth. We have more access to high quality data. We've got blockchain. So we know that we've got all these demand drivers, which are outpacing most likely the ability of energy efficiency to moderate that growth. So we do think, our study, the last study we conducted was in 2018. It's now 2022. We've had, unfortunately, the COVID pandemic. There's a lot more zooming, a lot more streaming, a lot more data center usage, and we see that in the energy trends from the big players, right? So what we know is that the ability of efficiency to historically moderate growth is probably losing steam. But there are technologies coming down the pike that could make a big difference. So for example, optical chips are super efficient for certain types of computations and workloads. There's a lot of room for improvement in reducing the amount of energy for cooling. The efficiency gains we're seeing on the software side and network device side are still really impressive. So we need to better balance this tension in our models and get better at looking forward and making some predictions because we're asked to do so more and more often by the media, by the public, and by policymakers. But it's going to take having better empirical data. And then finally, I'll close with just sort of, I'll be the first to say, as someone who's been in this field for 15 years now, the first study I did was the very first national study in the US, which was in 2007, a report for Congress at LBNL. That's when I cut my teeth in this field, and I've been in it ever since. In the last 15 years, we really haven't seen a strong growth in the number of researchers and research groups that are conducting data center energy analyses. And we know we have a problem because the different types of models are giving very different results. So I and others are recognizing it's time for this field to try to codify and adopt best practice standards. So in the building energy analysis community, in the transportation energy analysis community, in a lot of the other sectors that use a lot of energy, there have been, things like intermodal comparisons, best practices codified for research methods, much more data sharing, guidance documents like we have in the LCA community for how to conduct a data center energy analysis. And frankly, the other reason for best practices is there are many more publications coming out these days on the energy use of the internet or the implications of streaming. Peer reviewers who might not be experts in all the ins and outs of data center analysis also need best practices in order to gauge the quality of submitted work and to provide recommendations for improving it. So all of these are reasons that the community, it's small, it's thankfully growing, the models are getting better, the data sources are getting better. But my personal mission in the next year or two is to try to be part of a community that helps develop best practices so that we focus on where the improvements are needed, we recognize our weaknesses, we coordinate on our strengths, and we can all produce better numbers moving forward. Okay, so that's a very high level view of data center energy use, knowns, unknowns, how the numbers are made, and where the field is going. And I'd be happy to take questions.
Thank you so much for a really wonderful presentation. We have time for a couple of questions. They're in the Q&A.
I'm laughing because I'm reading the first one. It's a great question. So how much energy do high performance computing facilities use compared to data centers asking for a friend? So they use a lot of energy, and it's because they have very sophisticated high-end servers that are all interlinked for parallel processing. So there's a huge amount of computational horsepower, and with that comes a lot of energy use. But it's because of the sort of workloads that are being demanded, right? So that's an application which demands a lot of compute, and it's going to use a lot of energy. So compared to other data centers is a really difficult question to answer, in a satisfying way, and that's because data centers differ greatly in terms of their energy use characteristics. So a data center that is just caching websites and streaming video doesn't need a lot of computations, and for its installed server base will use a lot less energy than a high performance computing one. A data center running AI is going to use a lot of energy, right? These are all data centers. But if we were to just kind of take the average of all of those, definitely HPC falls on the high end. But in my opinion, that's, we need HPC to solve a lot of societal problems. So the other thing I always try to communicate when talking about energy use, and my opinion, just watching the trends, is that data center energy use is going to continue to rise. I don't think it's going to rise exponentially fast, but I do think it's going to rise. But we have to remember that it's rising to solve a lot of societal problems, which adds huge value to all of us. So hopefully that was a satisfactory answer on the first one. The second question is, I have heard of some companies like Microsoft looking into building data centers underwater to aid in cooling. Is this a legitimate effort, and does it seem like a good approach? So I've seen those trials as well. And let me just take a step back to talk about water cooling in general. So there is a big opportunity for data centers to just use more what we would call once through water cooling located next to cool water bodies. So there are some data center companies that are developing data centers on former industrial sites like pulp and paper mills or steel mills. Why were those facilities there? Well, because they were connected to a large power infrastructure and they had access to lots of cooling water. So a data center doesn't necessarily need to be underwater to take advantage of that high throughput cool water that you get by being close to a water body. And you can get pretty low PUEs with those approaches. Now, I have seen the few trials with the underwater data centers, and those are using a similar principle, right? Water's got a tremendous heat transfer capability. You can reject a lot of heat in water. So if you put the whole thing underwater, you've got very low energy for rejecting all that heat. Whether or not it's a good approach, I guess you have to ask, the data center operator what their needs are, right? I've heard some criticisms that it's difficult to upgrade the technology if if it's underwater. What happens if a server goes down? But there probably are ways that they can address those that they thought of. And yeah, maybe it'll work for certain types of data centers, but I'm watching it. It's not clear yet if it'll take off or not, but the general idea of using high throughput or, large water bodies like we've done for ages with power plants and industrial facilities can work for data centers. Okay, the third question is, what does the graph of data center energy use look like throughout the day week? Wondering how it compares to other energy demands. Another really great question, and it all depends on the type of data center. There is a growing interest in using data centers for demand response, meaning they could turn down their energy use at times when the grid is overloaded, or they could turn it up when there is opportunity to take more renewables from the grid. I know Intel has been looking into this. I think Google is claiming that they're doing it. And it all, hinges on that workload pattern that you have in any given data center and your ability to ramp it up or down or flatten it depending on the available power. Large data center operators that can migrate workloads between their data centers have more flexibility for changing their workload shape than do single standalone data centers for like an enterprise, right? For those, it's still bumpy, but it depends on all sorts of internal factors. So, I can't give you a general answer about what that shape looks like. If you'd like to email me, I can send you some technical articles with, workload shapes and power utilization shapes that I've seen in the literature for different types of data centers. But I know that this time of use, aspect to data centers is becoming a lot more important and getting more research and more attention due to the ability to use more or less energy on demand, use less when the grid is stressed, use more when there's more renewables, and overall that'll benefit the grid.
All right. I don't see other questions, so I think we will conclude here. Okay. Our seminar for today, and we thank Dr. Masney again for his presence and for the wonderful presentation tonight. Thank you.
Yeah, thank you. And if anyone would like to reach out, just Google me at UCSB with questions. I'd be happy to interact that way as well. But thank you for having me. It's been a lot of fun.
Thank you.
Okay.
Bye.
Bye.